Thank you for attending my virtual presentation for the 2020 NASPA conference. My name is Joe Thomas from the Cognitive and Motor Neuroscience Research Group at the University of Utah, and today I'll be presenting an experiment that looked at the role of air processing during skill acquisition as a function of practice schedule. A key component known to influence skill acquisition is the manner we structure practice. Typically, this is assessed by looking at differences in task performance between those who have trained in a blocked versus a random practice schedule. The conventional finding, which has been known as the contextual interference effect, is that the block group outperforms the randomized group during acquisition. This is because the block group only has to perform one task variation at a time, while the task constraints for the randomized group change from trial to trial. However, when tested at a later date, the randomized group tends to outperform the block group. Essentially, practicing under randomized conditions is believed to induce better long-term learning of a skill at the cost of short-term performance. The elaborate processing hypothesis has been offered as an explanation of the CI effect. It proposes that block learners are only exposed to inter-task processing during skill acquisition, meaning they only process and learn the constraints of one task variation at a time. Randomized practice consists of both inter and intra-processing, and this deeper engagement in learning allows individuals to compare and contrast task variations, which ultimately promotes superior task-based knowledge that can be recalled during a later post-test. This dual processing is also associated with increased cognitive effort related to the consistent task switching during the practice phase. Broadbent et al. Examined whether air processing may also play a role in the increased cognitive effort documented during randomized practice. Using a secondary task during the intertrial period, they found that those in the randomized groups took longer to complete the secondary task after making an error on the previous trial, indicating that the delayed response time may be related to air processing. In an effort to understand more about the role of air processing as a function of practice schedule, we examined whether prompting individuals to estimate their own performance underlies superior task representations that contribute to the better post-test performances often documented when individuals engage in random practice schedules. 84 participants were divided into two groups, differing on whether they were prompted to engage in air processing during practice or not, and whether they practiced under a blocked or random practice schedule. The task trained was a timing estimation task, which required individuals to hold a computer mouse down as accurately as they could to a predetermined target time. The three variations trained were 15, 17, and 1900 milliseconds. Feedback was provided after each trial, indicating how many milliseconds they were above or below the target. Every 7 trials, those in the air processing group were prompted to assess their own perceived performance by estimating how far over or under they thought they were to the target time. Following this, they received feedback to allow comparison between their estimation and their actual performance on the trial. The experiment was conducted over 2 days. The first day consisted of a pretest and 3 blocks of 70 trials during acquisition. Approximately 24 hours later, they returned for a 40-trial post-test, which consisted of a retention test of the same target times and a transfer test of novel target times. A main effect of block was documented, indicating all groups significantly improved performance across the acquisition phase. Additionally, as expected, results conformed to the traditional contextual interference effect for both our air estimation and non-estimation groups, indicating that the block group outperformed the randomized group during the acquisition phase. There was no effect of air estimations on the performance during this phase. During the post-test phase, we found a significant main effect of practice schedule. The randomized group completed the post-test with lower absolute error than the block group. However, no differences were found between the retention and transfer tests, and further, there was no effect of air estimations. Our results did not support differences due to error estimations in either the acquisition phase nor the post-test. However, there was a main effect of block in terms of error estimation accuracy, meaning that for individuals who estimated errors, both blocked and random practice groups were able to statistically improve their error estimation accuracy during the acquisition phase, showing a deeper understanding of their performance relative to the target. In this experiment, we demonstrated the contextual interference effect in a unique temporal motor paradigm. In an attempt to examine if task representations could be probed through the quality of error estimation, interestingly, we found no differences in post-test performance between those who estimated their errors and those who did not. However, the air processing groups demonstrated an improved understanding of their performance over the acquisition phase, regardless of whether they practiced under a blocked or random schedule. It seems plausible that, in fact, with the provision of feedback, even those who weren't prompted to process their errors may have done so anyway, which could support that air processing is an integral part of the skill acquisition process. Further work may benefit from using more sensitive task variations to improve our understanding of whether the quality of error estimations may relate to improved skill acquisition. Thank you for watching my virtual presentation, and any questions can be sent to my email at j.thomas@hsc.utah.edu.